but, well, why is it working? Hi everyone, and welcome to another video. So today we're going to be talking about if-else internals. We're going to be looking at how JIT handles if-else statements and expressions, and on top of that we're going to be looking at 4 different examples of if-else statements and expressions and see how they perform. And we're going to see some techniques how you can write your C# code that contains if-else statements and make them faster. So let's check it out. Let's go to the code. And let's start with a very simple example. So we have a function called C1 here, and it takes a single argument. And let's just say that if that argument I is equal to 1, then we're going to return 1, which we'll call an invalid state. And that invalid state is not throwing an exception now, because perhaps maybe we could do something with this -1. I don't know. We're not just gonna throw the exception yet. This is an invalid state, but this is a valid state. So you might imagine that this is not going to be called very frequently, but this is going to be our super duper happy path. So this path probably is the thing that we want to optimize for. So let's see what JIT generated for this case. And we're gonna compare our I to 1, and if this is not equal to 1, then we're gonna jump, and then we're gonna return I plus 1. Otherwise, we're gonna return -1. So already you can see that something is strange here a bit, because we have to jump in order to execute I plus 1, because this will jump if this is not equal to 1. So this condition got sort of rewritten into not equals really, and now in order to not execute the jump, we have to be equal to 1, so we have to go here. And that's a problem. So you might ask yourself, why is that even a problem? So it's just a jump, right? Well, the problem is that modern CPUs have a component called branch predictor, and then branch predictor has a certain default implementation that it follows. And in order to be able to explain that just in a short bit, we're gonna have to introduce 2 sorts of branches. So there's just 2 most of the time. So this is what we can call a forward branch, because we have to jump down in the instruction set. And also there's a different kind of branch, which is a backward branch, which will, for example, take the code from address here, and we're gonna jump up. So if statements are a forward branch, but for example for loops, while loops, and for each loops are a backwards branch, because you might imagine that we'll have to spin, right? So we have to jump up and then go down and jump up again. Now let's get to the problem of this. So modern CPUs and modern branch predictors assume most of the time that the default state for forward branches should be not taken. If they're taken, then we're gonna slow things down, and we're gonna probably have a misprediction already. So it would be good to rewrite this, if this is a hot path, to not take this branch here. So how can we do it? We can reverse this condition and say that if I is not equal to 1, then we're gonna return I plus 1, otherwise we're gonna return -1. And now, as you can see, this is correct, because now we're gonna compare, and if we're equal to 1, we're already gonna go to the -1, so we're gonna jump. But if it's not, then we're never gonna jump, and we're just gonna do return I plus 1, which is what we wanted, by the way. So now, perhaps let's put that to the test, because let's just see if the performance is going to be worse, or even if there's going to be any difference in performance. So I have 2 functions here called count simple 1 and count simple 2. They're actually identical, but the only difference here is this function C1 and C2. And these functions are the same functions essentially that we just wrote. So this is the function where I is equal to 1, and this is the invalid state. And in C2, we just reverse the condition, and now the valid state is inside the if statement, and the invalid state is outside. So let's see how they perform. You might also notice that they have an attribute called no inlining, and we're gonna get to that in a minute. Why is this? But for now, let's just measure performance. So we're gonna test this on a big array, and the first example took 24-ish milliseconds. Let's just run it again just to be sure. 23.2 milliseconds. Now let's see what's going to happen if we have our critical state within the if expression, and if statement itself. Let's just run it, and it takes 19.5 milliseconds. So it's already way better, and it's pretty stable. So the performance, characteristic didn't change. So it is faster, as you can see. So now let's go and let's rewrite this in another way, because as you saw, we have this no inline argument there. And let's now see why is that. So I have my function here, and let's add the loop on top of that, and let's see what's going to happen if my function is inlining here. And let's go here and let's check it out. So I'm gonna skip you the details, but we're gonna just see where this got inlined. So this got inlined specifically here. So this is the code that got inlined. And perhaps you can see it already, there's a problem. Although we have our hot state in the if expression, we're not gonna take this jump. We're gonna go here, but we're gonna take this jump, which is an unconditional jump. So the unconditional jump is still better than a conditional jump in terms of performance, but it's a jump nevertheless. So that's a problem. So we optimized one jump, but we created another. So this is effectively like a sort of like an almost else statement. And this is here because it's really difficult to have these two states all together in one simple like code base. This could be split into like two multiple sections almost, but the JIT compiler doesn't do it, so it is what it is really. And probably there's good reasons for that. But I don't know the reasons, by the way, because this could be rewritten in a fashion that would probably incorporate these two states without any jumps, but it's not being done like that. So that's a problem, and you might ask yourself, well, why we did the first example? Because there's no benefits, because we have two jumps now. We replaced one jump, but we did the other, so hey, that's a problem, right? Well, no. We can still use that, and let's move to another example that we have that could solve our problem. So what we have here is we have a counting function now, and that counting function does something interesting. So we're gonna start with the slow version. So the hot path is placed within a jump here, as you can see. But now what we're gonna do in this function is if the array element equals to 1, then we're gonna not count this element. Otherwise, we're gonna count the element, and let me just, modify this to count by 1. And we could rewrite this function in the following fashion. So if the array is not equal to 1, then what we can do is we can set the counter to 1 and then just count. Otherwise, we're gonna always set this to 0. So these two are equivalent, but the difference is that this is a jump, but this isn't a jump. And quite frankly, this will probably get optimized as well. So right now we're seeing sort of the same thing. It's gonna get us the same results, but this will use the hot path and will not generate any jumps, but this will jump. And let's measure maybe the performance of these two. So let's measure the performance of our count function 1, and let's add console write result, just to be sure that they're equivalent. So let's write out the result. Let's do count 1, which again will jump. So it takes roughly 12 milliseconds. And let's do another round. So it takes around 9 milliseconds. All right, let's do count 2. So count 2 takes around 9.7 milliseconds, and let's just do another one. So it takes 9.1 milliseconds. So that's good because we can already tell that this is probably faster, and I've went ahead and did a benchmark .NET run on a different data set, and on a different data set we got these results. So as you can probably tell, there is a performance benefit to this. So it's data dependent. So if you have a non-uniform data versus uniform data, you're going to have different results. But as you can see, there's results, and count 2 is faster by almost 50%. So that's good. So let's, for example, change this around, and let's use our random array this time around to check if we're gonna have any sort of benefits, or, you know, maybe it's gonna be worse, I don't know. So it takes 23.2 milliseconds, and this time around it takes 24. And let's go to count 2, which should be the more optimized version, and it takes 19 milliseconds. And let's run it again just to be sure, 20 milliseconds. So as you can see, there's performance benefits of using this technique. But now let's switch to yet another example, because right now, as you probably imagine, representing invalid state in that way is not really good. This sort of count that we had here, so this count here has its uses. You can actually find a lot of cases like that in NLP where you just don't have a invalid state, but you have a state that changes another state. But we would, for example, when we have an invalid state, we would like to throw an exception, for example, or return something else, or log something else. So let's now see how we can change this around, and let's see what's going to happen when we're gonna have an example which just has a return statement. So we're gonna have pretty much the same loop here. We're gonna have pretty much the same counts, and if the array element is equal to -1, we're gonna just return 0 and just, you know, let someone else handle that. And now what's going to happen is something really interesting, because all of our conditions, all of our branches got effectively reversed. So now we're gonna check against -1, and we're gonna see if this is equal to -1, and if it's equal to -1, then just return 0. So our jumps, our branches got rewritten in the inverse order. So now this is a hot path and this is not a hot path. So that's good, because that's what we wanted initially, right? And now we have it. Although this sort of return 0 is still probably not the thing that we would like to have. So let's, for example, do a throw. Let's throw a new exception. And as you can hopefully see, again, this state got rewritten correctly. So if we're equal to -1, then we're gonna go to the exception block, and this exception block creates the exception and throws the exception. So that's really good, because again, that worked in our favor. So now this is our hot path. But there's certain problems here. So we increased the stack space by a lot, and we did additional things here, because we have to reserve certain stack space for this exception to be able to happen. And since this can be called almost like 0 times in a program, so we're just increasing the stack space and doing certain extra work for nothing. So there's additional technique that we can sort of pull off here, and it's called a throw helper. So a throw helper is a special function which has to have a very special signature. So it has to return a void. It can take any sorts of arguments that you can, for example, but you have to return a void. Otherwise, it's not a throw helper and it's not gonna work. So what I mean by that? So if we have a throw function here, and let's throw something. So let's throw a new exception again. So this is a throw helper. So now if we're gonna replace that with a throw, and it has to be static. So now our function got rewritten in such a way that we still have the correct signatures and everything, but we have this call, you know, here, and all of the things that are related to exception throwing and the stack handling and stack, you know, increasing are in this sort of block here. So now we have a nifty function that basically is capable of like handling our exceptions. But let's just, you know, see what's going to happen if we do like the following. So now it has to return an int, and let's do a return 0, although we're gonna still throw an exception. It doesn't really matter now because all of the branches got rewritten incorrectly this time around, and this has become a hot path again, and this is the cold path again. So this is the preferred path. So as you can see, the throw helper has to be extremely specific. So it doesn't, no returns basically, what I'm trying to say you. And it has to be inlineable. So if you do like a no inline R parameter attribute on it, it's not going to work, because if you have a known inline attribute, then the JIT will not analyze this function at all, so it will not determine that it's a throw helper, first of all. And second of all, if you have like a very complicated throw helper, you can have a complicated one. You can even have multiple if statements with different sort of exceptions depending on the state that you're in. That's all good, but if you make it too big and it couldn't be inline, that's probably going to cause you problems, because that will not be a throw helper. So kind of keep that in mind. All right, so let's now do another example. So this is the last example, and I think this one is the most interesting one, because it's a really cool optimization technique that you can do with the JIT, but you have to know that it even exists. So let's go to another example, and let's copy this bit of code here. And this bit of code is super interesting for a lot of reasons. So I'm gonna have a flag here, which is let's just transform it into a field for now. So let's do like flag equals 1. And depending on the flag, let's actually do 4. Depending on the value of the flag, we're gonna pick the correct like branch here, and we're gonna write either 100 or 200. So what we generated right now is 2 console write lines. So we have effectively incorporated 2 branches, so we have to account for both. But there's a clever technique to be able to like eliminate automatically branches in your code, which is good because it decreases the code size. There's no jumps. The branch predictor has less work to do, and the performance will be better. So what you can do is you can create for example, function out of this. So we can convert this to a function. And as you can see, if this function returns a const argument, so a thing that will never change, what you now effectively did is you optimized the entire branch. So this code got just collapsed to console write line 100, because we know that we're gonna pick this path. And this could be like a static function, static read-only function. It can be a property, it can be an expression, and it can be a function. It can even be a function which takes arguments, but it has to resolve to something that's known at a compile time. So you can do a lot of things with it. So like I said, you can, for example, do int x, we can do return 4. We can do something with that x, but we cannot add this to h4 because it will not resolve correctly. So for example, we can do this. There's no problem with this. It's going to generate, but as soon as we're going to modify this, and this will not be a const, well, we're going to have a problem. So Now, as you can see, we're actually eliminated all of this code because we don't even believe that this is going to resolve to either 4 or 8. But if we would do like 3, for example, then it still works, which is surprising. But, well, why is it working? All right, so it apparently it's working, so that's cool. Oh, because this is still a const, and these two will get folded into a 4 because this is a const. Okay, so that makes sense. But if we would change that to a y argument and we would pass that y around, well, now there's a problem. And like I said, it could be any number of things, but it has to be resolvable at compile time. If it is resolvable at compile time, then it's all good. Again, it has to be inlineable, and without inlining this function, it's never going to be analyzed correctly. So it has to be inlineable. That's the reason. So how can we use this to our advantage? Because it's very cool. So for example, what we can do, and let me copy another method here, we can add a, for example, logging function of sorts, where we're gonna create a sum again, and let's add a int flag, and let's set that flag to 4, for example. So now, as you can see, we have this big function, we have our flag here, and our flag is set at compile time. So we can sort of enable logging by just having this flag here. So now we're logging stuff in this loop. So for example, we're logging errors. But if we turn this around and set this flag to 8, then we're just not logging anything, and we have a simple and compact loop. So we can sort of create this dynamic where, depending on the configuration flags that we have in our app or on certain different things, we can eliminate certain branches, and that's a very powerful optimization technique. Okay, so if you liked the video, leave a like, possibly subscribe, and leave a comment if I missed something, if there's a mistake here, and perhaps leave me some feedback about what you would like to see in the next video, because I have ideas, but maybe you have better. So yeah, thanks for watching, and see you next time. Bye!